Well, the first question in this video says, how many different 6-letter words are there? And remember, a word is just a letter arrangement. Doesn't need to be actually in the dictionary. Any ordering of letters can be made that use each of the following 6 letters exactly one time. Well, we know that if these 6 letters were all distinct, all different, like A, B, C, D, E, F, then it would just be 6 factorial. 1, 2, 3, 4, 5, 6. 6 possibilities, then 5, then 4, then 3, then 2, then 1. Multiply them all together. But we have some repeated letters. So it's going to be 6 factorial, but then divided by something. Notice we have 3 A's. And if all I did was rearrange these 3 A's, which, by the way, 3 A's can be arranged in 3 factorial different ways, 3 times 2 times 1, I could do that, and the word doesn't change because the A's are identical. And then notice also that I have 2 B's. If I took this AB, this abacab, and if I traded this B with this B, it is the same word, even though I've reordered the B's. And how many ways can I order 2 B's? 2 factorial, which is equal to 2. So that is the answer, but I guess I could simplify that a little bit. 6 factorial over 3 factorial would be 6 times 5 times 4. The 3 factorial would cancel over 2. So I will cancel the 2 with the 6 and give me a 3 up there. 3 times 5 is 15, times 4 is 60. So that's how many words you could make with those 6, how many 6-letter words you could make using these 6 letters. All right, now let's move on to computer talk. How many different bytes? A string of 8 bits is a byte. How many are there? Well, that's very simple. 1, 2, 3, 4, 5, 6, 7, 8. Each one of them has 2 choices, so it's 2 times 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 2. Make sure that's 8, 4, 5, 6, 7, 8. Yeah, 2 to the 8th, which I believe is 256. 256. Now, a little tougher. How many of these 256 different bytes start with a 0, 0 or end with a 1, 1? Well, let's draw a picture. 1, 2, 3, 4, 5, 6, 7, 8. All right, and the second picture is going to be that. So how many start with a 0, 0? Well, if this is defined, that's defined, those are fixed. The only variability comes in these right here, where I'm going to have 2 choices. 2 times 2, 2 for each one. 2 times 2 times 2 times 2 times 2 times 2. 2 to the 6th power. All right, how many of them end with a 1, 1? Well, there is 2 times 2 times 2 times 2 times 2 times 2. 2 to the 6th. Now, we do have to add those together, but we are not done, because we've counted this number. When we add them together, is going to be too big. There are some numbers that both start with 0, 0 and end with 1, 1, and those were counted in both sets. So we have to subtract the number of strings, bytes, the number of bytes, 8-bit strings, that start with 0, 0 and 1, 1, because they've been counted twice. And how many are there? 2 times 2 times 2 times 2. 2 to the 4th. So I'm going to add that and then subtract that. And the law that we just used, and I think, well, I guess those are small enough. 2 to the 6th, 2, 4, 32, 64. 2 to the 6th is 64, plus 64, minus 2 to the 4th is 16. So that's 128 minus 16, which would be, I think, 112. You can double check my arithmetic there. But the rule we just used here was kind of the additive rule of sets. It says that if A and B are sets, then the number of elements in A union B, which means the number of elements in A or B, like the number of elements that start with 0, 0 or end with 1, 1, is equal to the number of elements in A plus the number of elements in B, which is the number of elements for us, the number of bytes that start with 0, 0, add the number of bytes that end with 1, 1, and then subtract the number in their intersection. Because these were counted twice, in this set and in this set. So that just makes it work out.